Okay, welcome to lecture 1.6. We have been discussing transfer functions, right? And we discussed uh, some circuits on the last turn for which we derived the transfer functions. Today, we're going to do the same for a slightly more complicated circuit, which has three meshes inside. And let us try and do this in a way which is simpler as compared to what we have done before, right? So what we do in this case is to draw the equivalent circuit in the S domain. So if you draw the equivalent circuit in the S domain, it is going to look like this. So the resistance remains same, 1. The inductance becomes SL. Since L is 1 Henry, so it remains S. The capacitance is 1 by CS. Since it is 1 farad, so it's 1 by S. Similarly, you have 1 by S here. This resistance is 1, and here the source becomes VIS. It's a function of S, right? So this is your circuit in the S domain. And the three mesh currents, they are I3S, I1S, and I2S, right? So let us see whether we can, actually draw the find the transfer function, which is basically the output voltage here, V0S. So we are supposed to find V0S by VIS, the transfer function for this circuit. So let us see whether we can do this by writing the equations through inspection. So it is possible. And how do we write equations by inspection? We take a mesh, right? Let us, for example, take the first mesh, I1, in which the current I1 is flowing, and then we basically make this matrix in which we write down the impedances, the mesh currents, and then the voltage sources which are forcing those currents through those impedances. So the mesh currents we write here. So this is I1S, I2S. It's a column vector, I3S, right? And the first element here is going to be the impedance through which I1S is flowing, right? So this element here, the 1 element, is the total impedance through which I1S is flowing. So the total impedance through which I1S is flowing is S plus 1 by S. So write S plus 1 by S, right? Similarly, the second diagonal element here is the total impedance through which the mesh current I2S is flowing. So the mesh current I2S is flowing in this mesh, right? So this mesh. So this is 1 by S plus 1 by S plus 1. So this is 1 plus 2 by S. Similarly, I3S is flowing in 1 plus 1 by S plus S. So 1 plus S plus 1 by S. So these diagonal elements are talking about currents, mesh currents, which are flowing through those particular impedances. Now, the off diagonal elements, this is the 1, 2, row 1, column 2 element here. So this is the impedance that is common between mesh I1 and I2. So the impedance that is common between I1 and I2 is 1 by S. And if these two mesh currents are in the opposite direction within that impedance, then it comes with a minus sign. So in this case, I1S is flowing like this, and I2S is flowing like this through the impedance 1 by S, so it will come with a minus sign. If all your mesh currents are in either clockwise or counterclockwise direction, then all these off diagonal elements will be negative. Similarly, this element here is the element between impedance common between mesh 1 and mesh 3. So this is mesh 1 here and this is mesh 3 here, and what is common is minus s. So you have minus s, right? Similarly here, this is between 2 and 1, it is going to be symmetric, so this is minus 1 by s. This is a symmetric matrix. This is between 3 and 1, so this is minus s. This element is between uh, uh, mesh 2 and mesh 3, right? The 2 comma 3 element here and the 3 comma 2 element here. These two elements are between what is the common impedance between mesh 2 and mesh 3. So what is common between mesh 2 and mesh 3 is minus 1 by s here, minus 1 by s here. This is what is common between this capacitance is common between mesh 1, mesh 2 and mesh 3. So this is how we write this matrix down. And then the voltage sources, if the source is aiding the mesh current, it is positive. If it is not aiding the mesh current, it is negative. So there is only one voltage source, which is in mesh 1, and it is aiding uh, the mesh current. So this is VIS, right? And there is no other voltage source here. So these two sources are 0. So this equation actually gives you the equations that you would otherwise write through maybe a long procedure. In a single go, just by inspection, you can write it down. I think you have done this in your circuits course. If you have not done, I think this explanation is sufficient. So now to find out the output voltage, you basically have to find out the mesh current I2, right? Because that's the current which is flowing through this path. So if you find I2s, uh, VOS by VIS is actually equal to I2s into 1 divided by VIS, right? Which is I2s by VIS, right? So if you want to do this, you can do this by eliminating the second uh, variable here. And how do you do that? You by Kramer's rule, you can replace the second row of this second column of this matrix by this voltage matrix, and then divided by the determinant of this matrix. So the determinant of this matrix, this impedance matrix, is given by s plus 1 by s minus 1 by s minus s minus 1 by s 1 plus 2 by s minus 1 by s minus s minus 1 by s 1 plus s plus 1 by s. And your I2s would be replace this impedance matrix, replace the second column with the voltage vector here, and find out the determinant. So the I2s is going to be the determinant s plus 1 by s minus 1 by s minus s, and here you have VIS, and then 0, 0, and here you have minus s minus 1 by s 1 plus s plus 1 by s. So this determinant divided by this delta that you have actually written down here. This is your I2s. So you can open this up and you get I2s is equal to, if you open the determinant through this column up, so this is plus minus plus, so you can write this as minus VIS, right? If you open it from this column, you can write minus VIS into the determinant that you have here, minus 1 by s minus 1 by s minus s 1 plus s plus 1 by s, right? Divided by delta. So this is what you get when you open this determinant up. You can simplify this slightly more. I2s divided by VIS is equal to, so this minus you keep there, and you have here minus 1 by s 1 plus s plus 1 by s minus s into minus 1 by s, right? Uh, with the minus sign, so this is going to be plus divided by delta. So this is going to be, let me try to simplify this further. So you have this minus here and another minus here. These minuses will go, they'll vanish. You get 1 by s plus 1 plus 1 by s square plus 1, right? This whole thing in the numerator divided by delta. So I2s by VIS is going to be, so let me check this once more, 1 by s plus 1 plus 1 by s square. Okay, so this is going to be, okay, take s square common, so you have s square times delta, and in the numerator you can write twice s square plus s plus 1, right? Because you get 2 here, 2 plus 1 by s square plus 1 by s. So you get 2 plus 1 by s square plus 1 by s, and then you take s square common, you get 2s square plus 1 plus s. So that's what you have written here. So this is your transfer function. You have to simplify this further actually by writing the determinant delta um, from uh, from from this. You have to expand this and simplify this further. But basically, if you do this much also, you have found out an expression for the transfer function. So I hope this is clear. This is a slightly more complicated transfer function. We have not done anything new in this. We have actually applied the inspection method to find out the transfer function by using the inspection method in the mesh analysis for the circuit. We can do the same inspection, apply the same inspection method for nodal analysis also. In that case, uh, just like you wrote in mesh analysis, you wrote Zi is equal to V, uh, where Z are the impedances, I are the mesh currents, and V are the voltage sources. In a similar way, if you have to apply this similar method for nodal analysis, you'll write Y V is equal to I, where Y would be your admittances in the connected to the nodes. V would be the vector of unknown node voltages, right? And I would be the sources, the current sources connected to the node. So these are your sources, right? Here, the current sources. Here you have the voltage sources, right? For the mesh analysis. Here you have to convert the voltage sources to current sources. And within the nodes, uh, just like within the meshes, you have impedances within the mesh and mesh currents. In similar way, you'll have to write down admittances and the unknown node voltages. So you can check this method yourself if you want. This is also a very useful method, and you can quickly find out transfer functions for complicated circuits. So now let us move on. Let us go beyond circuits and try and see, because our aim is not to just write down transfer functions for electrical systems. We would like to do it for, as diverse a system configuration as possible. So the next thing would be like touching mechanical systems, right? How do we write transfer functions for some mechanical systems? What are the basic elements of a mechanical system, right? So building blocks, you can say, just like you have building blocks for electrical systems. In a similar way, you can have building blocks for mechanical systems. So what are the building blocks for mechanical systems? Okay, so uh, let us see mm, whether we have yes, in this we have the basic uh, mechanical system. Yeah, building blocks in this slide. So, so basically, again, you have three elements in a translational mechanical system. So it's called a translational mechanical system because we are talking about translation motion in this system. So you have three building blocks in this. Uh, to basically model three characteristics, right? So one is the spring block, the first one. So the spring block actually the governing equation between the force and the displacement, right? The force is equal to kxt, k times displacement, where k is the spring constant, right? So the force displacement relationship is F is equal to kxt. And you can also write down the force velocity relationship because velocity is the integral of displacement. So you can write F is equal to K integral of velocity, right? And if you want to find out the transfer function, if F is the output and X is the input, right? So basically, you can write down the impedance transfer function as F by X, which is K, right? Or otherwise, if, for example, X is the output and F is the input, then it is going to be X by F, right? And X by X, F would be 1 by K, right? Now, the second element is the damper. The damping constant F subscript V is basically the force, the damping force is proportional to the velocity, right? Just like the the spring force is proportional to the displacement, the damping force is proportional to the velocity. So 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 the governing equation is Ft, where Ft is the force applied, is equal to F subscript V into Vt, right? Where F subscript V is the coefficient of damping, right? Or you can also write it like this as a force displacement relationship, right? The applied force is equal to the coefficient of damping coefficient multiplied by dx by dt. And so if you want to find out the impedance, you have to transform this into the S domain. So when you transform this in the S domain, you'll write Fs is equal to Fv. This Fv is constant, and then you write Sxs, right? So if you have to find out the transfer function Xs by Fs, you'll say it is equal to S times Fv, and that's what we have here, right? Similarly, the third one is the mass, right? So you have three basic uh, elements in mechanical systems. And mass, you already know that force is equal to mass into acceleration. So force is equal to mass into the derivative of velocity, or force is equal to mass into the double derivative of displacement, and consequently, the transfer function is equal to ms square, right? So these are the basic building blocks for mechanical systems. I'll repeat. The blocks are M, mass, right? The spring, K, and the coefficient of friction, viscous friction, Fv. Sometimes this Fv is also denoted to write it simply as damping coefficient. Instead of writing Fv, we'll be writing D. So this we will do sometimes. We can use these two things terms interchangeably. Normally it represents by D. So now you have a mass spring damper system here, for example. It is actually modeling something. It is modeling something which has a mass, which has some spring characteristics, and which has some friction, right? It could be the model for any mechanical system, a simple mechanical system which has translational motion. So you're applying a force here, and consequently, this this mass, spring, and damper. You have to basically counter the three resistive forces, right, that you're applying. So basically, if you look at it uh, from the mechanics perspective, basically you have a force here that you're applying in the forward direction, and there is a displacement also, say for example in the forward direction. And if you want to draw the free body diagram, you have a force applied by the spring in the because the spring is going to counter the force is going to counter the displacement in the positive direction. So the spring is going to exert a force here like this. Similarly, the damping is going to exert a force. The damper is going to exert a force in the negative direction. It is going to resist motion, and of course, you also have this mass, which will which will resist motion. Uh, so basically, your Ft is actually equal to kxt plus Fv dx by dt plus md square xt by dt square. So this is the differential equation governing the mass spring damper system. And instead of writing the differential equation and then converting it into a S domain, what you can do is like what we did when we did this the same thing for circuits. You can actually write down the make the free body diagram. The free body diagram is actually all the forces you are showing together. You can draw the free body diagram in S domain, right? In S domain. So xt becomes xs, ft becomes fs. So and this kxt, the transformed equation becomes kxs, and this derivative s times fv, and the double derivative s square m. And then you can straight away write down the transfer function, because when you see this transformed equation, uh, you can say fs is equal to kxs plus fvsxs plus ms cap xs, and then you can write down your xs by fs is equal to 1 by ms cap plus fvs plus k, right? And this is what we have been trying to do here, right? This is what we have done here. We have actually taken the input as the force and the output as displacement here, and we have written down the transfer function as fs divided by ms cap plus fes plus k, right? This is for a simple mechanical system. Your mechanical system can also become complicated, right? It can have you can have 2 degrees of freedom basically, where uh, it is possible to have two displacements independent of each other, like in this case. And then you have to see how to find out the transfer functions for this system. So we'll see this in more detail in our next lecture. But what I would like to tell you is that the process that we follow would be very similar to what we have done for electrical systems. And one very important thing is that why we are doing this. We are doing this because, uh, like I told you in the beginning, an example like a car for which you have to design a controller, a self-driving car, right? Or even an antenna azimuth position control system. Those are electromechanical systems, right? Uh, and electromechanical systems, you should be able to model your electrical systems, you should be able to model your mechanical systems, you should be able to model find transfer functions for your motors, for other things, and only then you'd be able to say finally find out the model for the system, overall model of the system, and then uh, you can actually design the controller for it. So we'll see more about it on the next in the next lecture. Thank you very much for listening.